Number 2, find the power series and its interval of convergence for this series. Now, on the test, I saw students doing this multiple ways. Let's go over several ways, beginning with the easiest and fastest way. The easiest and fastest way to convert this function into a power series is to recognize that this one is in the form of the sum of an infinite converging geometric series. While we can adjust the lower index, we typically start with 1, and the series is a term plus that term times a ratio, and every subsequent term that we add has an extra factor of that ratio. In other words, the first term multiplied by the common ratio. And you can see that if we start with 1 with the exponent of n minus 1, the first term will be r to the 0 power, which is just 1. So the first term will be the first term. Okay, so if this geometric series converges, we know that the ratio has to be less than 1 unit away from 0. That is, the absolute value of r is less than 1. And if that's the case, a formula for the sum of that infinite series is the first term divided by 1 minus the common ratio. And this looks an awful lot like that. All we need to do is change the denominator to 1 minus the opposite of x. Our first term is 3, and our common ratio is negative x. Therefore, the series is the first term times the common ratio to the n minus 1 power, as n goes from 1 to infinity. And we're done. We can stop right there. And of course, there's an infinite number of equivalent ways of expressing this series, all of which were accepted. All right, now for the interval of convergence, using this fast and easy way of representing the series. We know that if it's a geometric series, it only converges when the absolute value of r is less than 1. So our series converges, the absolute value of the r value is less than 1. So this expression's distance from 0 is less than 1. We'll multiply all three parts by a negative 1. We have x is greater than negative 1, but less than 1. Do we need to check the endpoints? No, we do not. It's a geometric series which only converges under this condition. It does not include the endpoints. Geometric series' interval of convergence never include the endpoints. So we are done with this problem the easy way. If you did it this way, you might be wondering, how did some other people do this problem? This is one of the ones that we have memorized. Then we could have simply applied this transformation, a vertical stretch, by a factor of 3. And this might actually be easier than the other way and faster. This function is exactly 3 times this well-known basic fundamental function whose series we know and whose interval of convergence we know. This is the series for the well-known function, which is represented as negative x to the power of n minus 1. And with this transformation, we can just multiply it by 3. And it has the same interval of convergence. There was a third way I saw students do it, which was the most work, and we might as well just take a quick look, but I wouldn't recommend it for a problem like number 2. Some people actually created the power series from scratch. We recall first we need to know all these derivatives, then we need to know all these derivatives where our series is going to be centered. You need the wherewithal to know that we're centered at 0 in this case. It's the function 1 over x, which is centered at 1. Shifted 1 to the left. I'm not sure everybody would understand that. Then we would use this Taylor formula to derive the Taylor series. All right, when x is 0, what are all these values equal to? Substituting in 0 for x, all of these factors are just 1, so we're left with just 3. G's derivative at x equals 0 are these values for the first 6 derivatives and the general case. Therefore, the series will be, when n is 0, we have just f of 0, in this case g of 0, the function at 0, which is 3. Then when n is 1, we have the first derivative, which is a negative 3, times x minus 0 to the 1 power over 1. Then when n is 2, we have the second derivative, which we're down to here now, 2 times 3, times x to the second power over 2 factorial. When n is 3, we have the third derivative, times x minus 0 to the third over 3 factorial. When n is 4, we have the fourth derivative, times x minus 0 to the fourth power over 4 factorial. And if we simplify that, we get 3 minus 3x plus 3x squared, the first 3 terms. And then minus, and the 3 factorials cancel out, leaving us with minus 3x cubed. The 4 factorials cancel out, leaving us with 3x to the fourth. And we obtain our series, which we can then write in series notation, 3 times the common ratio of negative x to the n minus 1. Recognize that this is a geometric series where the common ratio is negative x times negative x. It's just negative x. And so the geometric series has a common ratio of negative x. And when you do the regular old, when is that common ratio less than 1, we get the same interval of convergence for the geometric series, which is the open series, the open interval from negative 1 to 1. You'll see, I think it's pretty clear for those of you who did this, whoa, you did not need to do so much work. And when some of you did, you made mistakes here with all this work. It was so much easier and faster to either recognize this right away as first term over 1 minus the common ratio, or to recognize that this is just a vertical stretch of factor 3 of the well-known function 1 over 1 plus x. If those things didn't come natural to you, then you want to study the first 2 ways of doing this problem that I showed you here, because that should be natural. It should be the first thing you do by instinct, and you should not waste your time doing this method on a problem like this. If you did, that's on you, and then you might be in a time crunch, and you shouldn't be. All right, I hope this helped.